Hello, this is Mariam Taha, and with me is Muhammad Sulaiman, and we're going to be presenting our final project for an advanced machine learning course on speaker diarization. So this is what we're going to be discussing in this presentation. First, we're going to introduce our problem statement. We're going to talk about the proposed solution. We're going to discuss our progress so far, both in the architecture and on the dataset. We're going to show you a demo of our project, and we're going to be talking about the individual member contribution. So for our problem statement, our project aims on developing a deep learning-based speech recognition model that can identify different speakers within an audio file. And the importance of this project is that it allows us to create diverse conversation datasets which can be used to train other deep learning models. It can also improve various applications like chatbots and sentiment analysis across different topics and areas. And it allows users with disabilities to discern the shift between speakers while watching YouTube videos and reading the captions, with the last one being the most important. So this is an example of our problem where in this video, for this example YouTube video, instead of only having the text, it would also have a speaker tag. Maybe not so much like this, maybe just saying speaker number 1, speaker number 2, and so on. This is a demonstration of our problem statement, with the first transcription not having any speaker tags to be able to explain which speaker is speaking at any given point, and the second one using speaker diarization has speaker tags corresponding to the speech or the text that they have spoken.
So for our proposed updates, we first started by running the literature review model, TitanNet. Then we proposed that we would combine it with Stol to make it end-to-end, but this didn't work because we couldn't find proper code for the told architecture to implement it. All of the code we found used very old Ubuntu systems and Coda toolkit, which was a part that we tried in Milestone 2 but failed. So we changed our objective, and instead of trying to combine it, we continued changing in the architecture. In Milestone 1, we had implemented a GRU unit in the architecture instead of the compilation blocks. For this one, we managed to include multi-headed attention between each of the mega blocks. So for the progress itself, we managed to change the baseline model up to 20 epochs, changing the condition block to GRU1 and checking the accuracy, then adding the multi-headed attention. So after implementing all of these, we noticed that the baseline model ended up giving very good accuracies after a certain number of epochs. So our goal with the GRU1 or intuition was making it give better performance from the first epoch. Versus TitanNet one, which was correct based on Milestone one, but it took longer to train. So we ended up saying that the baseline model is performing better. Then in this milestone, we added the multi-head attention between the mega blocks, but to our surprise, it gave way worse accuracy. It actually didn't really give proper accuracy because during the 3 epochs, it was oscillating in the loss. So the loss would go ups and downs and ups and downs. So it was oscillating actually in the same place. We tried changing the hyperparameters to modify this, but in the end, it still gave the same accuracy. So we weren't really sure why this is happening, because we thought that by using the attention we would make it closer to a transformer architecture instead of relying only on the GRU block for better accuracy. So even if it didn't really give better accuracy, we expected that it would still give proper accuracy, but it ended up not giving good accuracy at all.
Moving on to our progress on the dataset change. The original dataset that was used was LibriSpeech. LibriSpeech is a collection of audiobooks, so each audio file only has a single speaker, and each speaker is assigned a speaker ID that can be used for several audios. So this was used originally because it has a small size, and it was easier to deploy on TitanNet. The datasets that we have tested were Call Home, which is 30-minute telephone conversations between two speakers. There's also Vox Converse, which is an audio-visual file extracted from YouTube videos. Call Home, we were not able to use it because it required a specific version of Linux to run, which made it not easily implementable. And for Vox Converse, the format of the files that are available in the dataset were not compatible with the architecture that was used. So we have elected to use the LibriSpeech mix dataset. This is better than the LibriSpeech dataset because it involves audios where the speakers are speaking on top of each other, where not each speaker is speaking clearly at a time. There might be multiple speakers speaking at a given time, which is what happens in real life conversations. And additionally, it has more than 2 speakers in the audios, or in some audios there are more than 2 speakers, so that the model is able to detect more than 2 speakers per audio. So this is an example of our model. It had the 3 speakers speaking, which would be shown in the demo. and it was able to detect that there were 3 speakers speaking, and was able to detect when each speaker is speaking, and it highlighted each speaker in a different color. Moving on to our demo.
So for our project demo, we are using Nemo Toolkit to get the realization, because Nemo Toolkit includes the voice activity detection unit and the speech recognition unit with the speech impedance unit, which is SATANET that we are using. We wanted to avoid all of this by making our system work end to end, but that's a part that failed in Milestone 2. So while using the Nemo Toolkit, we imported our own audio file. Hey, how are you? Quite busy. And then we can check that the waveform gives us all black for this audio file. And then we load the configurations file of the Nemo for a meeting. And the important thing here is that it uses a sample rate of 16K. So we had to modify our original audio to match the same signal rate, because this was giving an error during the speech recognition. And then we let the models run on the input. And here we can see that it tells us that speaker 1 spoke from 0.4, and then speaker 2 spoke from 2.3, then speaker 1 again spoke from 5. And it labeled the waveform with green and blue for the speakers. And here we can see the transcript of what we said. So speaker 1 said, hey, then speaker 2 said, how are you? Then speaker 1 said, quite busy.
Additionally, because we have switched the dataset to the Libre Speech Mix dataset, which allows more than 2 speakers per audio file, we have tried testing it with more than 2 speakers. So this is an example audio with more than 2 speakers. Today is a beautiful day. I love summer more. And then we can see here the original waveform. Moving on, this is the processing till we reach where it says that we have 3 speakers, each one starting at a specific point, speaker 0, speaker 1, and speaker 2. And this is the new waveform that has the colored in when each speaker is speaking. And for our member contribution, this is what Muhammad has done, and this is what I have done. Thank you.